Well, this is part 3 of the finals review, and I'm gonna have to do this fast. I'm running short of time in trying to do all this. In this question, we have state the principle of conservation of momentum. Okay, the total momentum before collision is equal to the total momentum after collision if there are no external forces acting on the system. That is the law of conservation of momentum. Momentum is conserved. In the B part, okay, there is a collision here between a car and the deer, and the momentum of the car is its mass multiplied by velocity plus the initial momentum of the deer is 150 times 12. That is the total momentum before collision. Okay, notice that after collision the deer remains on the car, so you add their masses. Yeah, you get the total mass, and of course they're moving at the same velocity that we have to find now. So on calculation you get 27,000 for this term here when you multiply, and this is 1800. The sum of the masses is 1050, and now all you got to do is add those, divide by 1050, and you get 27.42 meter per second. Okay, let's move on. So that's the final velocity. In this second question, what is an impulsive force? Give a practical example of impulse. An impulsive force is a large force acting for a short time. Okay, a large force acting for a short time, that would be like punting in football, or kicking a soccer ball, or hitting the ball with a baseball bat. Now those are the examples. And then in the problem, a thin block of soft wood, mass given, a bullet is fired into it, and it passes through it, and the speed of the block after is given. You have to find the speed of the bullet as it comes out of the block. Again, a clear case of conservation of momentum. Yeah, I explained that already. Large force acting for a short time. Alright, that's the block, and the bullet is fired into it and then comes out. And oh no, I'm going to change that. 25 meter per second is the speed of the block, not the speed of the bullet. So I'm going to change that when I notice it. Okay. So mass of the bullet times the velocity of the bullet plus mass of the wood times the velocity of the wood is equal to the same quantity with the new velocities, right? Okay, so that's the mass of the bullet because you have to have it in kilograms. Velocity of the bullet, 621 meter per second. The wood is not moving initially, so its momentum is 0. And the final momentum of the bullet, that is the mass of the bullet. Nope, that is probably, yeah. Okay, so it is the velocity of the block, finally, that's 25. So we have to find the speed of the bullet as it exits. So we have to find VB prime. Okay, mass of the block times its velocity after, that's 25. So that's just that many VB prime plus when you multiply those two numbers, get 1.8. So now it's going to be 2.90 minus 1.8 is equal to that. So take the difference and divide by 0.00467. And when you do that, you get the final velocity of the bullet as it emerges out of the wood as 235 meter per second, considerably reduced, as you may notice. Right, number 3, state the conditions for static equilibrium. There are two conditions. The net force must be equal to 0 and the net torque must also be 0. Those are the two conditions. Now, this question about the meter stick is, it's pivoted at the 50 centimeter mark. Alright, read the problem and look at it. I've made both the diagrams. You have a 150 gram, you have a 200 gram. Mass of the meter stick is m, and the position of its center of gravity is x. We do not know that. In the second case, the masses are just interchanged. Okay, again the mass of the meter stick and its center of gravity unknown. Those are the pivots. First it's at 50 centimeter, then it's at 43 centimeter. Okay, so the 200 was first at 75, 150 was at 10. When you calculate the moments about the pivot, you get 200 times 75 minus 50, that's the distance, plus m times x minus 50. Those are the clockwise ones, and the counterclockwise is 150 times 50 minus 10, which is 40. Okay. Now take 5,000 to the other side. It becomes 6,000 minus 5,000, which is 1,000. That's equation 1. Now in the other situation, again taking the moments about 43, 150 times 75 minus 43 plus m times x minus 43 is equal to 200 times 33, which is 43 minus 10. Now you get on the right side 6600 minus 4800, which is 1800. That's equation 2. So if you divide equation 2 by equation 1, this is what you have on the left hand side. And on the right side you will get 1800 by 1000, which is 1.8. The masses cancel out, and you cross multiply. So you get 1.8 x minus 50 times 1.8 is 90. You have two x's, so you will have 0.8x, and then x is 58.75 centimeter. Substitute the value of x into this equation to give you the mass as 114.28 grams. Okay, the fourth question, what is torque? Torque tau is RF sine theta, where theta is the angle between the line of action of the force and the distance. Okay, so theta is the angle between R and F, as you can see. Alright, this problem at 500 Newton person stands there. Okay, the weight of the board acts right through its center, that's 100 newtons. The weight of the person is 500 newtons, and there are two supports. The reaction of the supports are F1 and F2. And the problem says that F1 is 3 times F2. Okay. Let's take this distance as x, and we're going to calculate the torque about the left end. So what is the torque of F2 at that point? 0, yes. Therefore, the counterclockwise torque would be F1 times 8 meter. And the clockwise, there are two. One is 100 multiplied by 4 meter, because 100 is exactly the center, plus 500 multiplied by this distance. We're looking for this distance. And that distance is 8 minus x. Okay, now all we have is the math. So that is 400 plus this would be 4,000. When you distribute 4,000 minus 500x. Okay, going back, remember that there are two conditions for equilibrium. The first condition is that the sum of these two forces, F1 plus F2, should be equal to the sum of the downward forces. So F1 plus F2 is 600. But F1 is 3F2, so you will get 4F2 is 600, which gives F2 is 150 newtons. So substitute that here. So you get 8 times 450, because F1 is 3 times F2, right? Okay. So now we could calculate x. X is 800 by 500, which is 1.6 meter. So the person is standing 1.6 meter away from the right side. Give one practical example to illustrate atmospheric pressure. Well, when a helium balloon goes up, the atmospheric pressure decreases. Therefore, its volume increases, and at some point it just simply bursts. Okay, that's a practical example of atmospheric pressure. There are several others. Okay, I'm talking about the helium balloon here bursting. Let me speed this up. Okay, and in the second part, you have a circular window, 40 centimeters. It can withstand a maximum force. We got to find the maximum depth to which you can take this submarine. Alright, force is pressure multiplied by area, but in this case the pressure would be the atmospheric pressure plus the pressure due to the water column. So that's why you have atmospheric pressure plus H rho g, which is the pressure due to water, multiplied by the area. In this case the area is pi r squared. Okay. Yeah, I just had a diameter in that question because it was not mentioned. So now we got to find H. So the left hand side, the force, maximum force is 6 times 10 to the 5. Area is pi r squared, so pi times, that's the radius in meters. And atmospheric pressure is 101,325. When you do the calculation, you get this number on the left hand side equal to H rho g. Okay, so now to find the height, or the depth in fact, divide that by the density of water, which is 1000 multiplied by 9.8. And on calculation, that gives 477.1 meter. That's how much below, that's the depth of the lake in fact. Okay. Number 6, define angular momentum. and give it a SI units. Angular momentum L is equal to I omega. Means it's the product of the rotational inertia I and the angular velocity omega. Those are the units. The solid sphere comes rolling down from a height of 4 meters. The idea here is that the potential energy at the top, at A, becomes equal to the total kinetic energy at B. Why do I say total kinetic energy? Because it has both rotational kinetic energy and translational kinetic energy, because the center of the sphere is not rotating, it's coming straight down. But at the same time, the sphere itself is rotating. So it has both types of kinetic energy. Potential energy is mgh. Rotational kinetic energy is 1/2 I omega squared. And translational kinetic energy is 1/2 mv squared. Now for a sphere, solid sphere, rotational inertia is 2/5 mr squared. And omega is v by r, so omega squared is going to be v squared by r squared. Now the r squareds get cancelled, the masses get cancelled, the 2's here in the first term get cancelled too. So finally we're left with GH is equal to 1/5 v squared plus 1/2 v squared. On the right side gives 7/10 v squared is equal to GH. Rearrange. V squared is 10 GH by 7. And so the velocity is square root of that. Now plug in the numbers. You get 10 times 9.8 times the height, which is 4 meter, divided by 7, which on calculation gives 7.5 meter per second. So that's the velocity with which it reaches the bottom. Brings us to number 7. A soccer player extends the lower leg in a kicking motion by exerting a force. Okay. And the angular acceleration is given. Remember, that's alpha. Alpha is 30 radian per second squared. The moment of inertia, which is I, is given. That's the rotational inertia of the leg. 0.750 kilogram meter squared. And here we could calculate the torque using I times alpha. It's 22.5. And we can now use the other formula for torque, which is perpendicular distance multiplied by the force. The perpendicular distance is given 1.9 centimeter, okay, which is in meters, converted into meters, and now you can calculate the force as 22.5 divided by that number, which is going to give a very big force. It is 1184.2 newtons is the force applied. Eighth one, what force must be exerted on the master cylinder of a hydraulic lift? Okay, this is the hydraulic lift. We know that a small force applied on the smaller side translates into a huge force on the other side because the pressures are equal. That is Pascal's principle. A liquid transmits pressure equally, and pressure is force by area. So the big force by the big area is equal to the small force by the small area. That's all we need. Okay, so rearrange, make the small force the subject, and everything else is given. Okay, area is pi r squared. Pi's cancel out, and the force is 2000 kilogram multiplied by 9.8. Okay, So that is the force times the small r squared, which is 1 centimeter. That's why it's 10 to the negative 2. And then the caps r squared, again in meters. And this, when you calculate, you get 136 newtons. Interesting question. A fire hose is turned on the door of a burning building in order to knock the door down. Alright, and the force given, the speed at which the mass of water comes out is 40, how much is that? 40 kilogram per second. Okay. And what's the minimum velocity of the stream needed? Interesting thing, you have to assume that the water does not bounce. That means the final velocity is 0. Well, I've just picked a picture that shows that with the force applied, a person's weight could even be balanced. That's how much force is being applied. Isn't that crazy? Well, coming back to the problem, you're asked to find the force. Force is mass times acceleration, and acceleration is delta v by delta t, right? Change in velocity by change in time. So I can rearrange that, and now I get mass per second, which is 40 kilograms. Okay, again, water doesn't bounce back. I told you this. Final velocity is 0. Therefore, the change in velocity is just going to be the initial velocity, which we are asked to find. Okay, 40 kilograms in 1 second. That's given in the problem. And so now there's a simple math. 1000 divided by 40 gives 25 meter per second. So that's the speed at which water is coming out of the hose, and that's a huge velocity. That's why the door comes down. Okay, brings us to the last one. State the law of flotation. According to the law of flotation, the weight of the floating object must be equal to the weight of fluid displaced. Weight of the floating object must be balanced by the weight of fluid displaced. So in this case, we've seen this problem before. We've done it before. The bear should float as it stands on ice. Right. The diagram will come up at the end. So in this case, the mass of the ice floe, mass is volume times density, and volume is area times thickness. I'm going to change it to 1 meter. Instead of 120 centimeter, I'm going to change the problem to 1 meter. Because I just copied and pasted this from what I did before. Okay. So now on the left hand side, what do you have on the left hand side? Again, I need to change the mass of the polar bear too. Anyway, okay. So on the left hand side, you have, this is the area of the ice floe times 980 plus 200. Okay. And on the right side, remember that this is area times density. Relative density is 0.98, therefore the density is 980. Because to get the density, you got to multiply with 1000. Okay, so that is area times density plus this is the mass of the polar bear, and this is the density of the seawater. Alright, and this is what I assume the thickness to be. Although the problem says 120 centimeters, I took it as 100 centimeters. That's why it's 1 meter. Okay. And remember that I'm just taking mass. That's why there's no G. So on calculation, this gives 200 by 54 meters squared. So I have to go back and change two quantities. I need to change this to 200 kilogram. because the numbers don't matter if you know how to do this problem. Okay, there it is. So I changed 200 kilogram and 100 centimeters. Thank you. I tried to do this as fast as possible. I hope you make good use of this.